Okay, now let's look at the topic error inverses. So what's the context for this is, suppose we have a matrix A, which is Cn cross N, and it's a non-singular matrix, okay? And we wish to find the A inverse. But we are not actually, we don't have access to the exact A. The measurement of A, in fact, is actually erroneous, and we got, instead of A, we got A plus E, where E is another Cn cross N matrix, uh, which is such that A plus E is also invertible. So A is invertible, A plus B is also invertible, E is small, but instead of A, we have A plus E. So the inverse which we are going to find is actually A plus E inverse. So now what will be the error in that situation is what we are going to analyze now. Now let's look at the error. The error is actually, error in the inverse is, we have A inverse minus A plus E the whole inverse. So if we take A outside from this this term, if you take A outside, it will be A into 1 plus A minus A inverse E the whole inverse. So you can use the formulation AB whole inverse is equal to B inverse A inverse. Using that, we'll get A inverse minus A plus A inverse E the whole inverse into A inverse. So we take A outside and we apply this rule, and this is what we get. So this is the error. Fine. Then we have already seen uh, if we can actually uh, if a matrix actually converges, then we can actually express its inverse as an infinite sum. This we've already seen. So here, if the spectral norm, sorry, the spectral radius of A inverse E, if it's less than 1, and then it is a condition for convergence. We've already seen that in the previous lectures. So here, let's assume that the spectral radius is less than 1. So the expression, I mean, the term I plus A inverse E can be expressed as an infinite sum. What is that infinite sum? It will be sigma k equal to 0 to infinity minus 1 raised to k A inverse into E the whole raised to k. So this is the expression for the inverse. It is derived from that. It's not exactly the expression for the inverse. Yeah, it is inverse. It's missing. This is the expression for inverse in terms of the infinite sum. Now what we do is we substitute. This is the error term which we had, right? And we substitute this infinite sum here in this term. So we'll get A inverse minus, instead of A plus A inverse E the whole inverse, we substitute. So sigma k is equal to 0 to infinity minus 1 raised to k. A inverse 0 A all raised to k A inverse. Fine. So if you take the first term of this, then this is, in fact, let's assume this is the sum which we have, right? The first term of the sum is putting k equal to 0. The minus 1 raised to 0 is 1. So an A inverse E whole raised to 0 will be I. And if you multiply that with A inverse, it will be A inverse. So I'm just taking the term k equal to 0. So in A inverse minus A inverse minus the rest of the terms from 1 to infinity minus 1 raised to k, the rest of the terms, and so on. So A inverse and A inverse will cancel. So A inverse minus 1 plus A inverse E whole inverse A inverse will be sigma k equal to 1. There is a minus sign outside. So that minus sign got absorbed inside. So instead of minus 1 raised to k, it will be minus 1 raised to k plus 1. A inverse E the whole raised to k A inverse. So this is what we get for this difference, the error function. Now we've already found an expression for the error. Now, using we know that spectral radius is actually the tightest lower bound, the uh, biggest lower bound which you can have for a norm, right? So if rho of A inverse E is less than 1, and now suppose that we have a matrix norm such that the matrix norm A inverse E is also less than 1. So if we take the norm of the error, which is norm of A inverse minus A plus E whole inverse, which is in fact, we can substitute for A inverse minus A plus B the whole inverse. We've already calculated that term. We substitute it here. So that be norm of k equal to 1 to infinity minus 1 raised to k plus 1 A inverse E whole raised to k A inverse. Now this is a sum, but inside the sum, so we can actually take the norm inside. So norm of a sum will be sum of the less than equal to sum of the norms, right? So you can take the norm inside. So that will be less than equal to k equal to 1 to infinity, the norm of this, which is in fact, we can then apply the submultiplicativity property also. So since we're taking the norm inside, minus 1 doesn't matter anymore because of the homogeneity property. So if even if you have a minus 1, the norm of that will be minus, we can take modulus of minus 1 outside and that will be 1. So this is norm of A inverse A all raised to k will in fact be, you can use submultiplicativity here. So again, that will be less than equal to A inverse E whole raised to k into A inverse. So ultimately what we have is yeah, fine. This is an infinite sum. Okay, this is an infinite sum of the form a plus a squared plus a cube plus etc. of that form. So the infinite sum, if the norm of the value is less than 1, that is a by 1 minus a. Okay, you can use this property and you can substitute the infinite sum by that value. So it will be norm of A inverse E divided by 1 minus norm of A inverse E into A inverse. So this is what you get as the uh, what you call the error between A inverse and A plus E, or A plus A inverse. Then you can actually, you have to find the relative error. So you can take A inverse to the denominator of on the other side. So A inverse minus A plus E, the whole inverse, norm of that divided by norm of A inverse is equal to norm of A inverse E divided by 1 minus norm of A inverse E if norm of A inverse, matrix norm of A inverse E is less than 1. This is for the final expression for the relative error. Okay, let's end the discussion here.